Do what on? Do that tomorrow? Tomorrow's Friday? Yeah?
We also have extra office hours.
Sebastian has extra office hours. Would like very short office hours sometime between 5:30 and 6:15 be useful today? I might be able to swing that. There. 3 to 4. Yep. So you guys, bring him a cookie or something because it's his birthday and because it's extra office hours. Very nice guy. Yeah, and I'll remind me at the end of class, and I'll double check my calendar to see if I can squeeze 45 minutes in there. And unfortunately, I won't be in town tomorrow. Yeah. Okay. Cool. So, and other than that, I mean, your only responsibility is your final project. You're almost there. Yeah. Yeah. So, and speaking of which, I mean, we'll continue to have office hours. My experience teaching MIT students is that suddenly your office hours get very quiet when the students are working on their projects as opposed to, doing homework. And it is true that we are even less likely to have an answer for you guys than we normally are for your course projects because you're all doing different, interesting, creative stuff. But it's fun for us to learn what you're up to. And there's no easier way to get a good grade than to essentially come to your instructor and make them feel like if your project failed, it was their fault. So, all of that is a good reason to stop by. Hopefully, were you guys able to see, I think every single person, I tried to put in some serious comments into your grade for the check-in. Yeah, so there's no excuse. Cool. Any other administrative things I forgot? It's pretty easy class administratively. Fabulous. So the last I saw you guys, we were talking about clustering and segmentation, which are these two nebulous terms that get thrown around quite a bit. And of course, our focus in 6838, which is not terribly surprising, is on clustering and segmentation techniques that know something about geometry. Right? And we had a very simple version of that, which was this k-means algorithm, which, if you recall, what does k-means do? You have sort of k cluster centers that you care about. You assign every data point to a cluster center, and then you re-average, and then you iterate. Yeah. So I think that's our story as we left it. And that there's sort of a nice balanced version of k-means, which is optimal transport. So there's order in the universe, all of our lectures in this class fit together, and life is good. Yeah? Incidentally, for fun, I threw on Piazza a link to actually one of my own research papers that is coming out hopefully this summer, unless I managed to screw it up by forgetting to revise until midnight yesterday, which I think we managed to glue together the last 5 lectures in this course in a pretty comprehensive fashion. So if you're looking for a really unintelligible piece of math, I encourage you to take a look there. Cool. So today, we're going to continue our discussion of clustering, and then we're going to move on to, remember our class, right? We're going to keep zooming out from a shape. Right? We started with curvature, then we looked at a whole shape. Now we're kind of taking shape into discrete pieces. And then next we're going to start relating shapes to each other, right? So we'll talk about rigid alignment, non-rigid alignment, mapping, all that good stuff. Okay, right. So in k-means, here's a purposefully vague summary of what the k-means algorithm does. Right? It alternates between 2 steps, where it assigns everything to its closest cluster center, and then it updates things with respect to an average. Now, and of course, in this class, I think starting in lecture 3 or 4, we talked a lot about the fact that there's geometry hiding everywhere in computer science, and it's not just Euclidean space. Right? And of course, there are many species of data for which notions like closest, farthest, and averaging make sense that aren't just vectors in Rn. Yeah? And that motivates many other algorithms. So in particular, if we just have a metric space structure on our data, it makes perfect sense to assign every point to its closest cluster center, if I have a data center point, and a data set and some set of cluster centers. And of course, the missing piece here is what does it mean to take an average? Yeah? And I claim that in any space where I have a notion of average and I have a notion of choosing my closest neighbor, I have a k-means algorithm ready to go. Yeah? And so, of course, the question that we should ask is how do we address that issue? Any ideas? What could we do? There are actually many ways out.
You could embed them in some space that has a defined average.
Yeah, you could say, if I don't have an average, put them somewhere that they do, right? We talked about embedding techniques, and that's a perfectly reasonable thing. What if we're in a compact set? This is for mathematicians. And you actually always have some notion of an average, yeah? So in particular, so you can ask this question, what does it mean to average a set of points in a metric space? Yeah? And there are many different ways to motivate what an average is. It sounds goofy. Actually, there's a SIGGRAPH paper from my friend Alyosha, about 10 years ago, that the title was The Power of Averaging. And it was some very specific image processing technique, but the title really stuck with me. It's kind of like, yeah, okay. But in any event, there are many ways to think about averaging, and as an optimization person, I like to make things more complicated. So let's say that I have a bunch of data points, x, that's a 1, through xk, and they're in Rn. And I would like the variational description of what it means to take an average. I'd like to write it as an optimization problem. How could I do that? Well, one way to understand the average of, yeah? Yeah, like somehow the average of a bunch of points is the most central thing. Yeah? And so one way to understand that is if I write this problem. It's the least squares problem for x, right? So here I take the distance from x to each xi, and I just sum them all together, and I optimize for x. What we'll show, I think I'll spare you guys the painful details, is that x is equal to 1 over, I guess, k times the sum of the xi's. In other words, x is the average. Here's the nice thing. So what did I need to cook up this problem? Well, I took a very particular notion of distance. I squared it, I summed them all together, right? And I said that the average of this set of points is the thing that minimizes this thing. Yeah? And this expression, this added up and divided by n, that was just a byproduct. Let's just, take the gradient and set it equal to 0. Okay, but this optimization problem, really all it depends on is a space with a distance in it. And that is a thing that I can lift to any metric space that I want. And so this is something called the Fréchet mean. It's also called the Karcher mean. For some reason, I think people in medical imaging like to call it Karcher mean. I'm not sure why. Apparently Karcher, I think he's still alive, and there's a bunch of quotes from him saying, like, please don't call it this. This goes back to Fréchet. But in any event, if I have a metric space M, and a bunch of data points xi in my metric space, then I can define the Fréchet or Karcher mean to be the point P that minimizes the sum of squared distances. Okay? Is this always guaranteed to exist? Well, no. I mean, there are plenty of spaces where you don't have an average. Let me give you oh, there's a biology class in here before. You see this DNA there. Okay, so let's say that I take the plane and I'm just being annoying and I cut out a little hole from the center of it. And this is a perfectly valid metric space. I have distance between every pair of points. And I write this optimization problem. Well, now you can see, for instance, here the plane minus a hole. This has a minimizer. I guess it would be a point on either side of the hole, but it's certainly not unique. And there are cases you can construct where there just doesn't exist a min. Right? Maybe there's a whole sequence of points that gets closer and closer to the min, but you never get there. I guess actually a simple version of that would be I don't include the boundary of the hole. But in any event, yeah, so this object is some general notion of what it means to take the average of a set of points. And this is useful in so many different contexts. It's a really popular notion, especially in the medical imaging community. So in that world, and we'll see an example of this in a minute, maybe I have a big collection of spleens. I personally do. I keep it in the back. There's I'm told lots of variability between different spleens. My spleen is different. I had a lot of cake. Sebastian's spleen is different. This birthday spleen is its own thing. And, so the same way I might want to ask about things like average and principal component and so on, I could ask the same thing about a collection of shapes. In order to do that, somehow notions like the Fréchet mean sort of say, well, if I can just start putting a metric structure on my space of shapes, then I can start to do stuff like take averages and do PCA. And these are some really cool techniques in medical imaging. So for instance, we have a big collection of brains. Okay, the more realistic one is some of them have Alzheimer's, some of them don't. And I'm trying to classify those two sets. Then maybe I look at the average brain in the Alzheimer's group, the average brain in the non one. This is a neurodegenerative disease, so the geometry is different. And you can actually see that when you take these sorts of means. So what do you need to be able to do that? You need to put a distance between shapes, which we're going to build up a few of those in the next couple lectures. Yeah? Does that make sense? And this allows you to do a lot of things. I have a slide here, which is from my understanding of a research paper in our own discipline, although apparently that's not actually what they do. but they could have. Which is, in fact, you already learned about one of these in Sebastian's lecture, right? So remember, optimal transport is a distance metric between probability distributions, right? And do you guys remember the name of the distance metric that they put in that space? I heard like a mumble where the constructive interference was roughly the word that I think I was looking for. Yeah, the Wasserstein distance, right? So that would be like I have a bunch of probability distributions rho sub I, and I want to average them. Right, then I can define something called the Wasserstein barycenter, which would be like over I, the W2 squared distance rho I. Right, so here, for instance, I have a bunch of probability distributions that are, for whatever reason, concentrated on two ellipses. When I average them in the transport metric, I get this thing that looks like the ring. And that's because this notion of average in W2 knows something about geometry of the plane. Yeah, and so if I wanted to cluster a set of probability distributions, now I can, right? Because I have the optimal transport distance, right? And I have a way to take, to find the center after I assign everybody to their closest mean. And I can iterate back and forth. Yep. Right, and so this idea comes up time and time again. Yet another place it shows up is like if I want to take a surface and cluster it into pieces, but specifically I want the pieces to look like planes or cylinders, right? Well, how could I do that? Well, one thing I could do is assign every point to its closest plane or cylinder in my collection, and then kind of refit the cylinder, which in some sense is solving some weird version of that, where one side of this distance now is a cylinder rather than a point, and iterate that way. And what you end up with is this technique called variational shape approximation, which can build Homer Simpsons out of cylinders and spheres. This is a popular technique out there for taking a shape and approximate it with some simple pieces. Okay, so this is just a simple means of taking k-means and making it work on spaces that aren't Rn. Yeah? What about discrete spaces? Let's say I'm on a graph. Does it make sense to solve a problem like this on a graph? So what would be the setup there? So I have some graph. Maybe I'm doing, my graph has some very connected component to it, and then maybe another connected component to it, and then one or two edges that go across, and I'd like to kind of cluster it into two pieces, right? So in this case, my k-means in some sense might be two vertices on my graph that I'm trying to place that somehow are central to these two cliques on the graph. Yeah? So how could I do that? Well, let's say that I identify, like, here's a vertex, and here's a vertex. These are my two means. So now I could take all the other vertices on the graph and assign them to the closest one and shortest path distance. That's perfectly well defined. That's sort of like the assignment step of k-means. And actually, this thing makes sense as well, right? But it ends up being a discrete problem, right? What it's saying is choose the vertex among the vertices of your graph that minimizes the sum of shortest path distances to all the guys it was assigned to. This is expensive algorithmically, but you can do it. And indeed, this is a reasonable graph clustering technique. Yeah? But that thing is expensive because just evaluating that value is kind of expensive. You have to compute a bunch of shortest paths. Yeah? And so there's a second technique, which is related but not exactly the same, called k-medioids. How many of you guys have come across this somewhere? So the idea of k-medioids is that I'm going to restrict my k-means, those means which are the cluster centers, to be one of my data points. So now I no longer have to optimize for, I don't have to solve the Fréchet mean problem anymore. But rather, I just pick out the data point because I have to evaluate all the pairwise distances anyway to to assign you to your closest cluster center. And I'm just going to use those to pick out one of the data points which is sort of the most central in each cluster. So in other words, I'm just going to restrict the domain of this min to the set of data points. So now it's just a question of evaluating a bunch of distances and choosing the smallest one. Yep. So this is called k-medioids because these central data points are called medioids. And especially in like graph clustering, this makes a lot of sense. Cool. So these are our clustering techniques. Here's a nice example of k-medioids in action. Maybe I have a bunch of shapes in a collection. Here's a bunch of people in awkward bathing suits, and I'd like to cluster them based on their geometry for some reason. You laugh, but this is like the most common technique you see in the geometry processing literature. I think in this case you would try to classify based on identity. because of course these things are using the metric space structure of the surface, and as we know, when people deform, they deform in a way that's largely isometric, right? So let's say that I wanted to do clustering in a shape collection. What would I need to be able to do that? Well, if I use k-medioids, then I just need a way of computing a distance between two shapes. Does that make sense? And it turns out there's many of these things. So I thought for fun, I'd show you guys one, which is pretty popular in practice, a good vocabulary word to know, which is called the Groma-Hausdorff distance. So now I've taken these people in awkward bathing suits and I've replaced them with a green ellipse and a yellow ellipse, respectively. Yeah? And I want to know when two shapes are similar to one another. Yeah? And remember that, like, you know, my people in awkward bathing suits, they can like dance, they can raise their arms up, put it sideways, whatever. Some of these are poses we don't really want to see. And when they do that, somehow we don't really care about their pose. We're just trying to figure out who they are. Yeah? So probably a reasonable way to compute distance would be to say that somehow two shapes are similar to one another if the pairwise distance between points, like as a function on the surface, if those two functions are similar to one another. Yeah? But there's a problem, right? Which is that these two surfaces aren't in correspondence. We don't know, like if I point on my hand, where that point is on somebody else, Colton. Yeah? And so we have to sort of solve that matching problem inside of computing a distance between metric spaces. Does that make sense? So the most popular way to do that is to measure something called the Groma-Hausdorff distance. This is a lot of notation for something quite simple. Okay? So the idea here, these two blobs are two humans, and so they're equipped with two distance functions. Yeah? And I want to know when, like if I have a map from one guy into the other, when is that somehow a map that preserves distance? And here's one way to do it, which is to say, if x and x prime are some distance d away from each other, like d sub x maybe, and y prime are some distance d sub y from one another, then if x goes to y and x prime goes to y prime, then dx should look like dy. Does that sentence parse? This is a fancy way of saying if this map takes these pairs of points to each other, their distances should look the same. Okay? And that's exactly what the Groma-Hausdorff distance is trying to measure. Okay? So let's take a look. So the interesting thing is that it's hiding an optimization problem for a map, but actually the thing that you care about is the objective value. You don't care about the map itself, at least for now. Yeah? And so remember that inf means minimize, sup means maximize. Okay? So on the outside, we're saying, look at any map from x into y. Okay? And now, so in other words, for every point here, I assign a point over there. In fact, I don't even think it has to be bijective, because typically you symmetrize, you add one going the other way. Okay, and I say, now I'm going to take any 2 points x and x prime over here. And I'm going to say, do you guys see what the objective function is saying here? It's saying the difference in distance between x and x prime and the distance between their targets under the map phi. Right? And so a good map phi is one for which this value is small for all choices of x and x prime. Yeah? So the score for map phi is what? It's the sup over all pairs x and x prime of this difference. So in other words, I choose the pair of points that makes the distortion and the distance value look the worst. And that number is the score of a map phi. That make sense? So the Groma-Hausdorff distance does one additional thing, which is it says that just by virtue of my two metric spaces not being the same, I can look at all of the possible maps and they're all going to have a little bit of distortion. Like they're just not isometric shapes to one another, right? So there's going to be some pair of points where these two numbers just don't agree, right? And so the idea here is I solve an optimization problem on the outside for over all maps phi that tries to minimize this sup value here. And that's going to be some positive number if they're not isometric. That make sense? Okay. And that number, that minimum objective value, is actually a distance. This is kind of amazing. It satisfies the triangle inequality and all that stuff, where you're looking at the space of metric spaces. Yeah? And so this is actually a distance between shapes. Do you get that? So I give you like the chubby dude bending over and the skinny guy standing up. Then this thing is a number telling you how far apart they are, which is saying the minimum distortion over all possible maps from one into another. Yes?
I feel like this wouldn't be that, well, I mean, how well does it work? Because my feeling is if you're taking the max or on them, like, couldn't that kind of like a weird metric for...
That's a great question, a fabulous question, especially because it happens to be one that I've studied for many years. Yeah, right, so to repeat Colton's question somehow, or at least to put words in his mouth to imitate the question I was hoping he asked. This is somehow a very brittle objective function because it only cares about one pair of points. Yeah, so like for instance, if I came up with a map from me into Yue here, and like, it's like 99% really good, but then by accident, like my middle fingernail goes to his eye. Like in a lot of computational, it never would. But in a lot of computational applications, that would actually be kind of okay, because like 99% of the surface gets mapped all right, and somehow that's better than like uniformly distorted map. And this norm doesn't see it. And you're absolutely right. That's a problem. So this one was studied for a long time because in theory it has a lot of really nice properties. You go to the Wikipedia page for Groma Hausdorff distance, you'll see lots of nice, beautiful theory. But there are actually two issues with it. One is that it's quite brittle. The other is that this is an NP-hard thing to compute. So in particular, even if my two metric spaces are discrete, they're just composed of like 10 points, I have to like iterate over all possible maths phi in order to compute this value. So we're going to come back to that second issue later. To go back to the first one, just for fun, since you asked, there are actually many different ways to do it. And since you guys are now all experts in optimal transport, I can explain the state-of-the-art one, which conveniently was written about by Solomon et al. So remember that in Sebastian's lecture, you heard all about measure couplings, right? And the idea of a measure coupling was it was a map, not a map, sorry, like a distribution, which was in the probability distributions over the cross product of my space in itself, right? With this property that like the integral of phi of x comma y dy is maybe rho 0 x, right? So like remember, this is like the plans of all the different ways I can scoop up mass with the constraint that I've got to, if I look over all of the targets y, first point x has to equal the amount of snow piled up at a point x, right? And similarly, if I integrate over all pi dx, I get rho 1 of y. Yep. There's a slightly more general notion out there of something called a metric measure space, where I have two things. I have not only a probability distribution, which can just be the area element, it can just be like surface area, but I also have a metric, and that they don't have to be the same. So let's say I have two of these guys, like x and y. Then I could look at the space of gamma, which is in the probability distributions. I like really want to write the real number symbol. Over x and y, where these are the two spaces that I want to map to one another. Yeah? And I could view this as kind of a fuzzy map, right? Like, so like, in some sense this is just a matrix of probability values, and maybe up here I have my stick figure and he's standing up, and over here he's standing down. These are kind of like the Blair Witch symbols, huh? I should like give them heads. Right, so when I do that, so like maybe I have a 1 here if this is like his hand and those two guys. Yep. Then there's a reasonable notion of distortion. So Gromov-Hausdorff distance, what would it do? It would kind of permute, it would view that matrix as kind of a permutation of the points of one guy onto the other, and then try to find the distance value that doesn't match the most. A different thing you could do is compute the expectation. So in particular, let's see if I can manage to get this right. So it's, so we're going to take a quadruple integral, yeah, to make this thing work out. Yep. So here's how it's going to go. Let's say that, I'm going to try and copy the notation here. So let's say that x goes to y and x prime goes to y prime. Yeah. Then I want to pay an amount of money, which is dx x prime minus dy y prime. Maybe squared just for fun. Yep. And so what is this value? So remember that this number is big if my map pi takes x to y and takes x prime to y prime, because I multiplied them together. So now I take a giant quadruple integral over dx prime dy prime. Yeah? And this is something that's like a score of a map. Yeah? And this is just like an alternative to the objective function there. And this is the average distortion as opposed to the max, right? So this thing is not subject to the problem that you were mentioning before. And you can optimize this thing, and it almost looks like the optimal transport problems you guys heard about 2 lectures ago. Remember, those are like linear in pi. The issue here is that there's 2 pi's. Yeah? And so what do you think the state-of-the-art algorithm happens to do in this case? I have some estimate of pi. It pretends like it's a constant for one of these two guys, optimizes for the other, swaps the two, and iterates. So it's basically just like an outer loop outside of an optimal, actually outside of problem 4 of your homework. For extra credit, you guys should code it up. It's an easy one. Cool. Great question, of course. These are, by the way, the next couple of lectures are on correspondence style problems, and these are problems that are very close to my heart. So unlike all this crazy exterior calculus stuff that I hate and can never get right, these are things that we know forward and backward. But in any event, whether you use Gromov-Wasserstein or Gromov-Hausdorff, you have some notion of distance between shapes. By the way, to make this thing have a triangle inequality, you have to take this fat piece of chalk and do that. Now it's the distance. But in any event, once you have that, things like k-meteoids are quite straightforward to implement. And they're used quite successfully. So this was one of the early Groma-Hausdorff techniques, which I'm realizing is hard to see on the projector here. But essentially, what you should get out of this figure here, what Facundo has done is he's sorted his database of shapes by category. So here's camel, cat, elephant, face, head, horse, lion. You say that 10 times fast? And what he's computed pairwise is the Gromov-Hausdorff distance, using some extremely expensive method. And you can see that there's nice little blue blocks down the diagonal. Essentially what this is showing you is that these shapes are closer to each other than they are to other categories. And that's what's allowing you to carry out this kind of clustering technique. Yeah? Cool. For a quick grab bag of other clustering algorithms before we move on to some more interesting stuff, one that used to be quite popular was really called agglomerative clustering. I think if you take machine learning class, you learn these fancy buzzwords for really simple algorithms. Agglomerative clustering, the idea is that I go through my entire data set and I find the pair of two things which are the most similar to each other and I glue them together. And then I just keep doing that until I have stuff that is the right number of clusters to what I'm looking for. Yeah? So a nice example of that, if you like these kind of nebulous mesh segmentation methods, is this one here. So they want to approximate a horse with a series of cylinders. So what do? They originally say, well, every triangle is its own cylinder, kind of vacuously. It's a very flat one. Yeah? And now we start taking adjacent pairs of triangles, and if all of those vertices in that little point cloud fit one cylinder really well, maybe I glue them all together. And I just keep iteratively doing this until I have the number of clusters I want. It turns out to be A, extremely simple to implement, and B, relatively effective for these kinds of techniques where you have some way of fitting a surface locally and you're trying to just glue them together to get a good approximation. You think you can say, I wrote down all these nice optimization problems, and you can say a lot about even k-means in some sense. You think you can say a whole lot about agglomerative clustering from an optimality perspective? Not really, right? This is extremely greedy algorithm. It's just gluing stuff together, and you kind of can never unglue. Yeah, and that's a problem. And there are many greedy algorithms out there. Another one is region growing, which is exactly what it sounds like. I don't think we need to spend a lot of time on that. And then typically, for every one of these clustering algorithms, maybe you glue that onto your favorite feature, which is trying to say that well, I don't just want nearby points on this horse to be glued together. I want nearby points with similar Gaussian curvature or something like that, right? So you can have this grab bag of the features that we already talked about. So if we step back, there's this giant zoo of different segmentation, shape abstract, sort of abstraction techniques out there, and it's very hard to compare them. They all have different properties. They're all kind of good at taking our favorite fan disk model here and replacing it with little blocky planar patches. And for a lot of applications, that's good enough. And so there are many different things to consider when you look at algorithms here, right? Like the cardinality, the number of segments you might get, the geometry of the different segments, topology, right? For instance, if you do k-means and descriptor space, you might get a disconnected segment on your surface, which is a little weird. But the one issue we have so far is remember that the first thing I whined about in k-means, the next time I just made it worse, it was there's no notion of optimality there, right? We wrote down that nice discrete optimization problem for k-means. The only problem is that we don't know how to solve it, at least to a global optimum, right? The k-means algorithm just gets you something local. Incidentally, there's a ginormous literature out there on how to take that k-means optimization problem, if that's just really what you care about, you don't want to change it, and trying to find a better solution than what you get with the basic technique. This is everything from clever initial guesses to no, I want the honest to goodness globally optimal solution and I don't care how long it takes to get it kind of thing. In which case, like if you take Pablo Perillo's class, you learn about semi-definite programming. There are even techniques out there that like try to relax to a convex problem and then recover with a projection, the k-means cluster and so on. Those are within the last 2 years and largely live in like happy theory land. How likely do you think it is that we'll ever discover an algorithm that gives you globally optimal k-means? Especially given the fact that I just asked you that question. The answer is not very, yeah? And in particular, to formalize that, it's actually NP hard. So like if I could find the global optimum of the k-means problem, that innocent little least squares thing I put on the screen last lecture, then P would equal NP. And there'd be a government conspiracy, they'd come, they'd take you away. Have you guys seen this movie? Yeah, yeah. I watched it as a postdoc in a math department. It required a lot of liquor. Right, so yeah, so the reality is that we really don't expect there to be a really good k-means clustering technique. And it's very unlikely because k-means is somehow the simplest way of writing down the clustering problem, that there's some other formulation that for some magic reason is easier to solve. But here I've given myself a way out by sort of, notice I use the phrase a lot, notion of optimality. And if I'm willing to lower my standards a little bit, then I can at least alleviate some issues with the k-means technique that really are like practical concerns, right? Like in particular, k-means is subject to local optima, and every time I run it, I could get a different answer, right? It depends on your initial guess. And then that can be quite problematic. So there's a whole other class of techniques out there in clustering that at least are decisive. They give you one answer, and they tend to have some notion of optimality after you relax your problem a little bit. And these things are known as spectral clustering techniques. They sort of serve two purposes. For one, sometimes they can account for the fact that you have like local versus global structure, right? Like k-means, the only thing k-means knows how to do is like cut things with planes, right? So if I cluster this concentric circle data set, I'll just get like an arbitrary plane going through it. So I can kind of take care of that by using notions of proximity instead of just cutting, the plane with a line. But the other thing it'll allow you to do is have some notion of being optimal, at least within a factor of what you were looking for. And that can be useful in certain contexts, right? Like if you really have a mission critical segmentation system and you just do not want it to fail, then k-means is really a bad choice, right? Because every once in a while it can just give you it could just garbage, yeah? And so the earliest example of that, although this is like one of these algorithms that like shows up time and time again, and every time it does, somebody else gives it their own name. There's many examples of that. My favorite so far, we collaborate with political scientists, and when they measure the shape of a political district, they use the isoperimetric ratio, which is perimeter squared divided by area, right? This is minimized for a circle. And they call it the Polsby-Popper score after two political scientists in the 90s because they invented it. Anyway, okay, so, right. So in this case, we'll talk about a particular technique called normalized cuts. Sometimes people call it, spectral clustering, or it has a lot of different names. But I think the basic idea is as follows. So let's say I have a big point set that I want to cluster, yeah? And what I'm going to do to cluster it is I'm going to compute a pairwise similarity matrix W. So Wij is large if I and j are close to one another. So it's not a distance matrix, it's a similarity matrix. Does that make sense? Let's say I had a distance matrix. What would be a reasonable way to get a similarity matrix out of it? Yeah, 1 over it, e to the minus it. There are a lot of answers here. Yeah. And these are things minus, yeah. Minus is going to be a problem because that'll screw up the positive definiteness. Actually, I'm not sure it will. We'll come back to that. Let's think. Okay, so let's say that I want to solve clustering, and specifically into two pieces. We'll call those pieces A and B. We'll use C for cluster. Okay? Or cut, I think, actually. Then a reasonable score for my clustering is maybe that I look at all of the edges that cross from one side of the cluster into the other. Right? So like I is in set A, and J is in set B, and I sum all of these things up. What happens if this score is high? What happened? I took a pair of scissors and I cut apart things that were similar, right? That would be a bad clustering. Bad. And so what we really would like to do is to have a low cut score. Why wouldn't I just optimize C if I wanted to get a low cut score? What's the lowest score I could get? 0. I could just put everything in one cluster, then there are no edges that cross over. Yeah. So we have to counteract for that somehow, and there are many different ways to do that. By the way, this is one formulation, and there are many others that kind of look like this, where like maybe one of these sums is over a slightly different set, and the math ends up being the same. These are this is just one example of many. So one thing you might do is define something called volume. Notice the difference between the cut score and the volume. The volume here, I look over all of the things in set A, and all edges in A, including the ones that are within A. Right? And I sum up the W's here. That makes sense? So let's say that let's say I'm doing graph clustering. Or not even graph clustering. Let's say that I'm just clustering, a data set, and I've got 2 nice clusters that I'm trying to find, right? And I want to cut like this. Yep. Then the cut score is going to account for just like distances like these, whereas the volume is also going to look at distances between the points on the 2 sides, right? And so this is like roughly trying to just count the amount of stuff on one side or the other, whereas the cut score is trying to count the amount of stuff that crosses from one side to the other. Does that make sense? Then the normalized cut score is this thing that I have here, where it says I'm going to take that cut score, and I want to normalize it. In other words, like if I just have the volume, that one of these sets is empty, somehow that's not a desirable output. So I'm going to kind of normalize for that by dividing by the sum of the volumes of the 2 sets. Notice there are a lot of engineering decisions, right? I could have divided by the sum of the values, and all of these are roughly the same. There's very little difference between these. But this is the one that was in the original paper, so we'll go with that. Cool? Everybody get the setup? So in an idealized world, I'd like to find the cut, so the partition of my set into A and B that minimizes this normalized cut score. What do we think? Can we do that in practice? No, because it's NP-hard, because all of these problems are NP-hard. No matter how you write down clustering, it's NP-hard, guaranteed, unless it's like boring. Okay, so we'd like to somehow solve some version of this problem, but we can't quite get there. And so normalized cuts does a really bizarre but clever substitution. Okay, so the basic trick is this. So I'm going to define. So let's say for a second that I did solve this problem. So I do know A and B. Yeah. Then I'm going to define for each of my points. I'm going to define a particular number, which is xi. I'm going to say he's one of 2 things. I'm going to say if xi happens to be, if I happens to be an A, then I'm going to define xi to be 1 over the volume of A. This is a definition. This is a weird definition. It's just a vector, 1 number per point. Yeah. And if I is in B, I'm going to make it minus the volume of B. Okay, this is just some weird vector. But notice that, like, if I know this thing, I know my partition. Yeah? Okay. So, and why do I know my partition, by the way? Like, let's say I give you X, how could I read off the partition? This is the positive and negative stuff. Yeah? Assuming that W is positive. That's where this breaks down. Okay. Great. So here's going to be the really strange thing we're going to do. We're going to write our normalized cut score in terms of this weird vector X, and then we're going to drop the constraint that X has to take this weird form and just say that X is a signed vector of real numbers. That's the magic trick that happens in the normalized cut technique. Is it weird? Yes. Is it principled? No. That's the end of my comments. So in particular, let's expand a few values here. So let's write something that almost looks like the normalized cut score, but just for fun, I'm going to put an extra factor of this thing. Notice that this is just like sort of a constant. Yeah. So let's say I write an expression that looks like as follows, which is the sum over I in A and J in B of Wij V of A inverse plus V of B inverse, and just for good luck, I'm going to put a square. So if that square weren't there, do you guys see that this is the normalized cut score? I just kind of dropped in the formula for C. Nods, some kind of acknowledgement. Okay. Why would I do that? Well, take a look. So I just defined this funny vector X, and now I have numbers that look an awful lot like what I wanted. And it's sort of reasonable. Okay, so why did I put the square here? Well, because I'm going to try really, really hard to make this look like a least squares problem, and somehow that's as close as I'm going to get. Okay, so in particular, I'm going to do the sum over I in A, J in B, of Wij. This is V of A, but notice that I is always in A, right? So this is secretly xi for any of the i's that I care about. Sneaky, huh? And similarly, okay, well this is plus V of B, and there's a minus there, so this is minus xj, like that. Squared. Now do you guys see why I've defined this x? What does this thing look like? This looks like a Laplace operator. Yeah, no matter how hard you try to escape in this class, the same thing keeps coming back. Yeah? Okay, so, but it would almost be a Laplace operator, except there's like this kind of weird asymmetric sum going on here. Yeah? But let's say I and j are both in set A. Then what is this difference? 0, right? Because xi and xj in that case would both be the volume of A. And similarly, if I and j are both in B, the difference is, there we go, 0. So in particular, I can just drop the subscript, and actually the value doesn't change under this particular definition of x. Weird, huh? Okay. So in particular, this is actually just the sum over all ij, wij, xi minus xj squared. Cool. And now if we expand the square, this is exactly the graph Laplacian with weights w, right? This is exactly the expression we had before. Yeah? So this is really just x transpose Laplacian x, where your Laplacian is the d minus w, and d is a diagonal matrix, right? Where dii equal to the sum over j of wij. You guys remember these formulas? These came up several times already. And this just comes from this squares expression. Does that make sense? If I'm skipping steps and you want me to fill it in, I can. It's just expanding the square. Cool. Now we're in good shape, right? We like Laplacians in this class, and we just found one by making a weird definition, but we're going to forget that for now. Okay. Cool. So let's do some more weird math. So in particular, let's take the norm of x with respect to this diagonal matrix D. Yeah? Ugh. So in other words, let's compute the following quantity. We're going to see why we're doing all this stuff in a second. Like that. So remember that D is sort of the diagonal matrix where it's like the sum of the row sums of this W guy. So in other words, this is really the sum over I of xi squared times dii. Cool so far? Okay. And of course, this thing by definition, so this is I xi squared. This is the sum over j of wij, like that. Okay. And now I'm going to do something a little sneaky. Surprise, I know. Which is, I'm going to take this sum over I and I'm going to divide it into two parts. What do you think those will be? There's only like one thing with two parts here. the sets A and B, yeah? So first of all, what is xi when I is in A? Well, it's the volume of A to the minus 1, yeah? So this is volume of A minus 2, yeah? Times the sum over j, wij, and similarly, j, I and b. Now it's what? It's vb, well it's minus vb inverse, but it's squared, yeah? So this is v of b to the minus 2, sum over j, wij. Cool. But notice that a sneaky thing happens. Since this is a constant, I can now move this sum past, and what do we get? So this is the sum over all I in j in A, the sum over all j in everything of wij. This is exactly the volume of A. Yeah? So what do we end up doing? We just ended up canceling out these minus 2's. Yeah? So what we get is that this is volume A to the minus 1 plus volume of B to the minus 1. Now we're in good shape. What is the normalized cut score in terms of Laplacian and x transpose dx? Don't all speak at once. Well, remember that this value up here is almost a normalized cut score, except that I squared. But conveniently, the thing I squared is canceled out there. Yeah? So it's equal to 2x transpose Lx divided by x transpose dx. Sneaky, huh? Okay. Everybody else me so far? By the way, I think in my slides I forgot this factor of 2. That's my bad. It depends what definition of Laplacian you like, whatever. Okay. So here's the thing. Let's say that okay. I wrote this in this really funky form, and this is totally cheating, right? Because what did I need to get this expression? I had to define x in a very specific way. Yeah? And as long as I define x this way, then this is the normalized cut score. But x is exactly the thing I don't know, so this is just a total lie. Yeah? So in other words, what is my optimization problem? It's sort of like min of this expression such that x takes this form up here. So how could I lower bound my optimal objective value? I could drop that constraint, right? If I do a minimization problem and I remove a constraint, then my objective gets lower because I have fewer things holding me back. Yeah? So this thing I can optimize. Yeah? What is this thing? This is a Rayleigh quotient. Yeah? So I want to optimize it. What am I going to get? I'll get that, I guess, 2Lx equals lambda dx. Right? That's what happens when you minimize ratio of two quadratic forms. This is from lecture 2. Yeah? And we're done, right? This is the thing we know how to optimize. So this is the normalized cuts algorithm. What you do is you start by defining this funky vector x, and you define your whole problem in terms of this weird vector x. Right? And then really your optimization, yeah, I knew I forgot it too. Your optimization becomes minimize this thing subject to x taking this weird form. I drop that constraint, and now I can optimize for it by just computing the smallest eigenvalue of L, or I guess the generalized one, which is something you guys are really good at. You did it a lot on your homework. Yeah? And, oh yeah, I guess you can add a constraint that x sums to 0 if you want. That just like kind of centers it. But at any event, when you do that, you get an eigenvalue problem. And then how do you think you get your two clusters? What was that? Yeah, you just look at the sign of the vector x, and that's about as good as you can do. And it turns out this is like a totally reasonable approach. Oh, by the way, this constraint that it sums to 0 is quite easy to see. It actually just comes from the definition of x, right? Because I put volume of A and minus the volume of B, and so they end up kind of canceling out. Okay. So is this globally optimal for the normalized cuts algorithm? No. Does this give me an unambiguous output to clustering that's the same every time I run my code? Yes. And there's some notion of optimality in that at least this number, after I drop that weird, that binary constraint on x, at least this number lower bounds the value that I wanted for my clustering, my normalized cut score. Yeah? And so this is a very popular technique in practice. And indeed, I think you can actually show that this value is within a constant factor of the one that you really wanted. It's not that far off. And so, for instance, here's a k and n graph. So I think here W is very simple. It's just 1 if you share an edge and 0 if you don't. And you can see the colors are the graph clustering, that it did exactly what we would expect, right? It found the two kind of cliques and cut right across. Yeah? So this is a really effective algorithm, and it's an example of a larger class of techniques called spectral clustering, where essentially you construct some Laplacian out of a similarity matrix, you compute its eigenstuff, and you cut. Yeah, and these are extremely effective things in practice for any number of reasons. One is that they kind of are inspired by a clustering method, is the phrase I would use. But we'll see a lot of other properties that also kind of support why this is useful. The obvious question you should be asking, what's the difference between this method and k-means, other than, most everything? What's the difference in output? K is 2, yeah? And it's not obvious how to extend these algorithms to more than 2 means. In fact, that's where this literature starts to get kind of heuristic again. So for instance, people will talk about recursive bipartitioning. So if k happens to be a power of 2, one thing I could do would be cut it in 2 pieces, cut each of those pieces in 2 pieces, and so on. It's sort of like the opposite of agglomerative clustering in some funny sense. Or you can, I think the more popular technique is to say, in some sense, there's a k-means algorithm hiding here, which is that I compute the first eigenvector of L, and then I do 2 means, which kind of necessarily are the 2 extremal points, and then I cut halfway. Right? That's kind of what this algorithm is doing. That would be a really terrible implementation of it. So one thing you could do if you want k clusters is to compute k eigenvectors, and then do k means and that kind of funny eigenvector embedding, right, which we already talked about. And it's actually a pretty standard method, I think, for clustering. When you do that, you are not guaranteed to get connected components. When you do this with 2, you actually are, but that's a heavy-duty theorem. But there's so many different reasons why this algorithm you would kind of expect to work beyond just this motivation. One is that the smallest eigenvector of Laplacian is this extremely well-studied object. It is called the Fiedler vector. You guys, are you familiar with this? And there are actually topological results about the Fiedler vector, which are super cool. So here I have this dumbbell thing, and the color is the Fiedler vector. I actually wrote code. This is code that I wrote, and it makes color. But in any event, if I cut this thing in 0, notice it's like right in the middle of the barbell here. And so, for example, one topological result about this is if L is the graph Laplacian, and I cut at 0 on this thing, then necessarily I will get 2 connected components on my graph. That is not obvious from this linear algebra problem. And so it kind of makes sense to make 2 partitions. Like you don't accidentally get 3. Like you could imagine a scenario where you're like -1 and then positive and then negative again, and that just doesn't happen. If this sounds familiar, remember we talked many lectures ago about the maximum principle for Laplace operators? That's exactly what's going on here, right? There's no local maximum, which is why you can't get these isolated clusters. And in fact, people do just take the surface Laplacian, this good old cotangent formula, and use it for clustering. So here is one early example where what they do is they take the Laplacian and they just divide it into regions on the surface where the eigenvector has positive and negative sign, and notice that actually gives a fairly meaningful clustering or like segmentation of the surface. These objects, if you'll recall, they're called nodal domains of Laplacian, and there's all kinds of beautiful theory that tells you that they have nice shapes, their boundaries aren't too crazy, all these kinds of things. In fact, there's a theorem by Courant. You might recognize Courant as also the name of the math department at NYU. The Courant's theorem, at least the Courant's theorem in my particular discipline, is that the kth eigenfunctions of Laplacian has at most k nodal domains. So you kind of know roughly how many eigenfunctions you have to compute before you get the number of partitions you want using a technique like this. Yeah. Right. Mm-hmm. That's true. In the graph, it's a little bit of a trickier matter. I think it's harder to control the number of segments you get. Yeah. Mm-hmm.
I guess I'm kind of curious about like if for the clustering algorithm, you have this very tangible idea of like what clusters are,
Mm-hmm.
and then we drop the constraint on X. Does that have some geometric interpretation of how the Laplacian clustering differs?
Yeah. I'll come back to you on that one. I'll have to think about it. Yeah, I mean, you're absolutely right that somehow we've relaxed X. And in fact, what we've done is replace an integer with a real value. And I don't know geometrically the right way to think about it. It's a good question. Yeah. No. Cool. All right, to highlight one more issue that I want you guys to kind of kick around in your head for the next couple lectures, and we're going to come back to it later on once we've talked about correspondence problems. One of the major issues with these algorithms is that I run them. What have I told you how to do? I've told you how to take a single piece of geometry and break it up into segments. And now I could take a whole data set of people like this person who's walking and sitting and jogging, I guess. And I could run my same segmentation algorithm on each. And there's an issue, which is that in effect, when she's standing straight up, she's finished her deadlift, she's ready to drop it back down on the ground. Her knee is now flat, yeah? So all of these clustering algorithms that are purely geometric in nature are not going to put a segment on the upper and lower part of her legs. Because there's no reason, there's no inspiration there, yeah? So there are many ways to resolve this problem. We'll talk about one now and another later. The one that we're going to talk about later is that let's say that I observe all three of these poses at the same time. And I don't just want a segmentation, I actually want a consistent segmentation. In other words, somehow the fact that I see her in more than one pose gives me a clue that even though her leg is straight here, it's going to be bent in a second and I should put a segment there. Yeah? And so this is a great instance, segmentation is a great instance of a problem where if I have a whole data set of shapes, I can do much better than if I just have one. Yeah? Of course, that suggests a very different approach, which is machine learning. And of course, it's important to note that actually I think this is a totally reasonable juncture to insert learning. Because often when we talk about segmentation, we really are talking about meaningful parts, right? I'm talking about like knees and elbows and thighs and legs and so on, right? I'm not talking about like areas of constant mean curvature. And so I think it makes perfect sense to say like, no, segmentation really isn't a purely geometric problem. There's some semantic component, I suppose Aaron wouldn't like that term. There's some, some intuitive component here that's somehow not captured by these geometric techniques we've talked about. Right, the obvious counterexample is the brain, where there are very meaningful folds that are associated with different functions in your brain. But I'm not even going to attempt to name because I'm sure I'll get it wrong. Indeed, what we might call supervised segmentation algorithms have been around forever, especially in the image domain, but also on shapes. So one of the earliest ones was proposed in 2010, and by all accounts, this really sparked off this huge literature we now see in SIGGRAPH, CBPR communities on taking surfaces where somebody has just painted on labels on different parts and trying to learn that labeling. Yeah, so this is one nice example from Vangelis Kalogerakis and his friends at the time at Stanford or maybe Toronto, I guess. And here, as an input data set, you're given a bunch of shapes, like a bunch of octopi with, I guess, head and tentacle labeled here. Do octopi have heads? In any event. Or like chairs have backs and legs and seats and so on. And if I have enough of these things, I might be able to learn interesting geometric features that could predict the segment moving forward. Yeah? But there's always a big problem in these geometric learning problems is that they're not entirely learning in the sense that like, machine learning algorithms fail some random fraction of the time. And if I got a segmentation of this surface where like 95% of the vertices on this jug really were labeled jug, but like every once in a while it's labeled dog or something, I kind of know that's bad just because it's not a continuous big object. Right, so there's still some topological kind of geometric component missing in these algorithms. And so for instance, what was proposed in this paper was to use what's called a conditional random field. When I was doing machine learning, this was the popular tool that was going to solve all of the machine learning problems. It has since been replaced by, I guess, deep stuff. But in any event, the idea of a conditional random field is actually much more intuitive, I think. So the basic idea here is that when I want to label a mesh, there's sort of a unary term and a binary term. The unary term says I have a bunch of features on every vertex, right? Heat kernel, curvature, all the favorite things we've already covered, right? And I just do a simple regression, like SVM or whatever, that tells me that like, when I see heat kernel that looks like this, I think it's the leg of a horse, yeah? And so a very, very simple segmentation algorithm would just iterate over every vertex, run that thing, and just, that's the label. And the problem is you tend to get like little isolated regions where you get the wrong label on the surface. So to counteract that, we say that it's not just something that locally looks like the label, but that a good label is one where if essentially two neighboring vertices should have the same label as much as possible. Yeah? And then they solve a small optimization problem. This is sort of a standard trick in graphical models, and outcomes are really nice, smooth segmentation. The problem with this particular technique, if I recall, is that they need a very large data set of labeled shapes in order to pull this off. But think about what that means. That means like if I want to segment horses, I need a big data set of horses with labels on them, which is not so easy to find. It's not like Instagram, we don't know how to take like horse selfies and paint on the labels yet. And so these things are of some limited usage. So of course, people have studied lots of like unsupervised versions of this, or maybe I have a few horses with labels and then a big data set of horses without labels or what have you. This is a big literature, and I encourage you guys to dig around the last couple of years. Especially I think SIGGRAPH proceedings and computer graphics is where you see a lot of this stuff. Before somebody asks, of course, shortly thereafter, people did put it into a deep network starting in about 2017. So this is actually fairly recent stuff to do surface segmentation with these kinds of tools, and there's much to be done. And there's some unsupervised techniques. So we're going to talk about this more a little later. And like essentially this question of if I have a whole data set and maybe I don't know how to segment any of them, then just the fact that I have this data set of things in different poses can help me find consistent segments that are meaningful and kind of stabilize this problem. That makes sense? Cool. All right, so that concludes segmentation. So in our last couple minutes here, we're going to move on to a different problem, which is now, remember, we're stepping back farther and farther. We've done everything we can do on one surface. Now, finally, we're going to have two. Yeah? But they're going to be two of the same surface for today and for next time. Yeah? In this case, two bunnies, which are our favorite surface in computer graphics. I think it's sitting on Mark Lavoie's desk, or at least it was at some point. Actually, no, I don't think that's true. I think now this is at the Computer History Museum in San Jose. But in any event, a very typical situation, whether you are taking a 3D scan of a bunny or you have your favorite LiDAR or whatever car thing driving down the road, is that you get a lot of 3D scans of the same scene. But what's going on? Like when I'm driving my car, well, my camera is moving with the car, so the scene keeps rigidly moving. Yeah? So like from the perspective of the car, it's not a bunch of collections of points sampled from the same object. It's a bunch of collections of points sampled from objects that are rigidly displaced from one another. Yeah? And this problem of taking multiple point clouds of the same scene and gluing them all together is called registration, or alignment, I think is a simpler term. And registration is one of these key problems in geometry that everybody should know. Incidentally, it also appears in machine learning, where instead of registration, they call it transfer learning. Yeah? So in transfer learning, what do you do? Like I have all of the photographs, all the product photographs on Amazon.com. I have all the product photographs on Walmart.com. Yeah? And I'd like to kind of glue them all together, but there's actually a little bit of bias in those two data sets. Like maybe people at Walmart like to take photos of cereal boxes from the side, or whatever. Yeah? So they're not quite sampled from the same distribution. And so a very simple thing you might do is try to co-align these two clouds of points, in this case, images, so that I can safely take inference drawn from one data set and transfer it to the other. Yep. This is a pretty common technique. So of course, in these particular slides, I borrowed from a lot of people. This is a classic problem, so there's a lot of slides out there to steal from. And the basic task in registration is you have multiple scans of some object, and you're trying to basically just glue them all together. And there are many variations of this problem. Right? Sometimes you have rigid shapes, like I really have this chair, and I'm just scanning from multiple angles. Maybe you have a non-rigid shape, like I'm tracking you moving in front of a camera and I'd like to put everything in the same pose. Or in the worst possible case, maybe you have a bunch of shapes for the same category, like a bunch of chairs. But I think at some scale, there's some correspondence. Like there's some legs that match, and even though they're not the same geometry. Yeah? We'll see that matters quite a bit. So like in today's lecture and next time, we'll talk about mostly rigid alignment. So like just rotating and translating one shape on top of another. And then we're going to broaden that to non-rigid alignment. So this will be like taking one shape, like distorting it a little bit, and then lining it up on the other. And then finally, we'll talk about intrinsic alignment, where, like, for instance, this Groma-Wasserstein problem, where I don't want to try and just glorp one shape onto another because I'm going to fail. So instead, I just want to find some mapping that preserves features in a kind of smoothish way. Right? Those are kind of multiple scales here. And this is a very typical piece of the 3D reconstruction kind of pipeline, right? So maybe you have some acquisition device like this crazy geodesic dome that they have at USC. And of course, the problem here is that each of these cameras is at a different angle. And so when they photograph Halley's face here, they, what you end up with are not a bunch of things that I can just average together. And so you register them, and then you try to extract one mesh with lots and lots of detail. In fact, I think this photo light stage thing that they have also extracts some really cool stuff, like reflectance on your face, the BRDF, and so on. You really can like simulate a photorealistic character, which is pretty neat. So our rough plan for talking about the basics of registration, we'll talk about a very classic algorithm called iterative closest point, ICP. We'll talk about some of the variants of the ICP algorithm. We'll see ICP is one of these algorithms where like you can prove a theorem, which is that it like works every time you initialize ICP with the solution to ICP. But there are like a lot of variations out there that were intended to make ICP more stable. So ICP was introduced in 1992. I happen to remember that because I'm involved in a court case right now involving who invented it. It wasn't me. I was not old enough to do that yet. Right, so in any event, for about 10 years after ICP was introduced, there was this huge academic literature of like, oh, well, sometimes it fails in this case, so now I'm going to fix that case kind of thing. And applied to different things, right, like bones and medical imaging and teeth, or non-rigid shapes, or 3D scans of the outdoor environment. All of these require slightly different variations of the ICP problem. For the latest spin on that, you should talk to our student Yue, who just submitted some research involving ICP problems. And then finally, we'll talk about some related things. And I use the word related here in a little bit abstract fashion because it's an excuse for me to talk about some problems that I really like. So a very different version of an alignment problem is something that sometimes is called multi-reference alignment. Those of you who went to a PhD defense this morning in the maths department may have heard this term. So this would be like, I have a bunch of signals that are on a line, right? Like I keep observing, some function, but every time I get it, it's cyclically permuted. Like it's really a signal in a circle, but the circle keeps rotating. Yeah, and so I'd like the average signal, but to do that, I need to co-align them. Like I need to find the right rotation for everything, so they're in the same frame, and then I can average them together. This is called an angular synchronization problem. It shows up quite a bit in microscopy. So have you guys ever heard? We'll digress for 10 seconds, and then we'll do ICP. Have you ever heard of cryo-electron microscopy? Got the Nobel Prize a couple years ago. Ah, you're killing me. You guys need to read some science news. So cryo-EM is a really neat technique for imaging biological macromolecules. I think you hear about that today, huh? So in biological macromolecules, you have this problem, which is, okay, so how do we do DNA? You crystallize it, it has this kind of regular structure, so you can kind of image it at a macro scale and infer things about the micro scale. That's like roughly what goes on with DNA. But that was Watson and Crick, that's old news. And apparently not very nice people, right? One of those two. But in any event, in cryo-EM, I'd like to image some weird protein, and it just doesn't crystallize. It's a weird shape. It doesn't behave. So what do? I submerge it in some water, so it's floating around in some water that you don't want to drink, and you freeze it. So now what you have is a bunch of samples of your protein suspended in a bucket of water, and now I take a razor, which in my mind, because I'm a theoretician who's worked on this problem in the past, I think of like Gillette, but I'm sure it's more complicated than that. And you take a very thin slice off the top of this little chunk of ice. And so what do you get? You get like a little microscope slide with little samples of this protein that are frozen into place. And I put that into the electron microscope. And what comes out? Well, if you think about it, so remember what the electron in case you didn't know, what the electron microscope does is it takes line integrals, right? So you have this molecule, which is some density, and you put some damn thing into the top, and the fraction of stuff that comes out of the bottom is roughly proportional to the density of the shape. Right? That's how like X-ray works. So what happens? I took an X-ray of this molecule, so here's my microscope, here's my collection thing, here's my cryo-EM sample. I hit it with the beam. And what do I get coming out? I get the projection of my molecule onto the plane of the microscope. Yeah? This is super cool, huh? What's the only problem? Well, there's two. One is that these are really small molecules, so the signal-to-noise ratio here is like 0.1%. It's ridiculously small. It basically looks like TV noise. But that aside, the other issue is it's kind of like taking a photograph, but like forgetting where you put your camera. Right? Like remember, how did you get that sample? You just like had this sample of this molecule floating around in water. You just have froze it at whatever point in time it happened to be at, and then imaged it. Yeah? So the multi-reference alignment problem, these sort of ICP, is this totally distant problem from ICP, but it turns out to kind of look the same. Essentially what it's trying to do is to recover where your camera was, given not like a photograph of your scene, rather a projection onto a plane. Which is really crazy if you think about it. Yeah? So anyway, your homework for next time is to read a little bit about cryo-EM, because it's super cool stuff. You should look online. They're like 3D macromolecules you can reconstruct. They got a Nobel Prize. But in any event, our starting point for rigid alignment in 3D is much easier. So you're given two data sets. Typically they're point clouds, or we're going to have a lot of schematics in our next lecture involving curves. And your job is that you have like the green curve and the red curve, and you'd like them to sit on top of each other. I guess these are colorblind, unfriendly slides. I apologize. The top one is the green one, the bottom one's the red one. Right, so mathematically, how could we do that? If I have a bunch of points P sampled on one guy, a bunch of points Q sampled on the other, then what I'm trying to infer is a rotation matrix and a translation, right? So that when you apply the rotation and translation to the P point cloud, they kind of sit on top of each other. That makes sense? So, first of all, let's do some degree of freedom before we pack up our bags now. How many correspondences do we need to determine R and T? Like, so the first question is that we don't know what pairs of points correspond between these two curves. Let's say somebody just clicks them for now, which, by the way, is what actually most rigid alignment looks like. How many do you need in 2D, say? 2. 3, yeah, right? Because there's, how many degrees of freedom are there? Well, you have R is 2 by 2, T is 2 by 1, right? So there's like 3 vectors, kind of, that you need. So you need 3 correspondences to determine this. So there's the next question. Is how do you get correspondences? This is going to basically motivate our lectures for the next several weeks. But what will be the simplest thing? Find corners, yeah, find interesting points and try to map them to one another. But specifically in the rigid case, like if I have a pretty good initial guess, what's a pretty good correspondence? Just your nearest neighbor, right? Like, you know, if I'm trying to align a rectangle to another rectangle, there's one, and here's like a slightly off rectangle. I didn't manage to draw that very well, but imagine that we're closer. Then actually a totally reasonable map here would be to just kind of take closest points like that, and then to align. Magnus looks suspicious, and he should, and we're going to see that this algorithm doesn't work terribly well. But it can get you, it'll get you closer than where you were. So for instance, here's my initial guess, right? Here are 2 curves. I took the closest points. You can see this does not look like a rigid motion. But whatever, maybe I find the best rigid motion in the least square sense that kind of fits this matching pair of points. And what do I get? Well, I don't get exactly what I wanted, but I got something that was a heck of a lot closer. Yeah? And now what could I do? Do it again, right? Take closest points. And now these closest points are a heck of a lot more reliable than the ones I started with. And my alignment improves. So here, in fact, I think I did it. Yep. And that is the ICP algorithm. It's really, really simple. Every point chooses its closest point. You find the rigid motion which fits that bad map as best as possible. But now just by virtue of moving stuff, right, like for going from left to right here, your closest point actually can change when you do that. So then you iterate.
Does it have any sort of constraint?
No constraint.
What if it warps into a weird shape?
So there's no warping to be had here, right, because this is always going to be rigid. I'm going to find the least squares best fit rigid match. But you're right, this is one of many suspicious aspects of this algorithm.
So it's very brittle to initialization.
It's extremely sensitive to initial guess. Yeah? Like for instance, what's a good example? Like let's say that here's a rectangle, here's another rectangle, and by bad luck I initialize them to be just exactly across from each other. Well, just by symmetry this thing is already stuck, right? It's not going to go anywhere. Yeah? But that said, the typical thing to do, and indeed if you look at the user interface in a lot of medical devices, what they'll do is they'll ask the doctor to like click a few pairs of points, because it's like not all that unreasonable to ask somebody to like click the eyes, nose, and mouth. And that gives a pretty good initial guess for ICP, and then it's just used to kind of round it off a little bit. And it's a perfectly reasonable tool for that. Right? So the algorithm in its full glory is here. Right? You choose a bunch of points on one surface, you match each guy to its closest one, you solve this optimization problem, which we'll do next time. Good, because I didn't feel like doing it today. And then you iterate. And this is this algorithm which goes back to 1992. And it is worth knowing because literally everybody in geometry uses this thing all the time. Yep. And in fact, even in some funny context, so like in a couple lectures we'll talk about this functional maps technique where you have functions on 2 surfaces, you want to align the space of functions as a way to map from one surface into another, and you'll see that ICP actually is hiding in there. It's just in that case your rigid motion is in this very high dimensional Fourier space rather than in the space of rotation. Cool? All right, so next time we'll start with the thing I was ever so slightly stalling from doing today because I didn't want to do it, which is to solve this optimization problem, which is saying that I marked the pairs of points that correspond, find the least squares best fit, rotation, and translation. Anybody know the name of this problem, by the way? Procrustes problem. You know who Procrustes is? Bed. Yeah, indeed, right? There's like, I think it's what, Greek mythology? There's a guy, Procrustes, and you know he only had one bed, and so if you were a guest at his house and you're too tall, you go to sleep in his bed and you just cut your feet off. I'm not sure what the point was, actually. I should go back and read. But in any event, so we'll solve the Procrustes problem at the beginning of next time, and then we'll talk about the many variations of ICP that are out there in the literature. And these are things that are used every day in robotics and are worth knowing. Okay? So with that, we'll see you next time. Don't forget.